Let's talk about it later. Yeah, so. Okay. That's it.
Did you update the test grades for last test?
Yes, I think so. Did I not?
Like, I saw my final grade, but my test grades are still the same.
Someone else also asked me, was I supposed to change test grade? Did I say something like that? I think there's a second person asking.
Usually test grade changes with like extra credit and then.
It shouldn't change. I usually don't change test credit. Do I? Why is the confusion there? So give me a second. Let me just set this. Okay, so.
I guess I wasn't sure how that worked, whether you applied it to the test itself or you just applied it to the final grade.
Apply to the final grade. Maybe long back, I think 2 years back, I used to curve the exams and not do anything about the final grades.
On the first test, I noticed like when you like physically graded my test, you had a certain grade. And like when you submitted the grade, it was different.
Really?
So you maybe added onto that.
It shouldn't be. These days I don't do this. Like what you're saying is that I curve the exam, or that's what you expect me to do. No, I don't remember midterm. Like I could have done something that was very specific to midterm 1. But typically what I do is that everything happens and the total grade I curve based on extra credit. Exactly, I think I can.
And that should be more helpful, though, right? Because you include the homework, like missing points from homework would also.
Yeah, exactly. Yeah, I think so. That is better. But you're the second student in this course asking, so we are only 5 to 6 students. So I'm wondering what the confusion is. So what I do is, no, I don't hesitate to change midterm 1. So that's why it could have happened that midterm 1 I changed. I don't remember myself. But typically, no, nothing happens. All the grades work, and this is your total grade. Right? Whatever comes out, total midterm, homework, and extra credit. Right? Those are only 3. And the final exam, if that is one. Like in the end. And then I do 100 minus total. Right? And then so this is, so if I give the whole thing, then you get a full percent, right? So this is your curve, if you want. That's your score, final score, if you want. But I decide to give you only a little. So usually, for example, I think last time it might have been 20%. So 20% means it's 0.20. I multiply this. And then I put on a y to that. So y is your extra credit. Or so, for example, if you got 70 out of 100 in extra credit, I'll make this 0.7. So out of 0.2, when you multiply 0.7, it becomes 0.14. Right? For this particular situation, y times a is 7 into 2, 14, right? So you get only 14% of your final of the what I of whatever you lost instead of 20%. That's how it works. So, and this part I did. This is what I had not done. And when I said that I have not curved it, the A I had not chosen. So I chose the A and return back. Usually what I do is I look at everyone's grade. If anyone is on the border or someone, I try to help them to cross that border. So A is very personal, like this is fine, but I look at the whole class and do it. But whatever I decide on A, everyone gets it. right? So usually I pick whoever is on the border, I try to push them up. But nothing specific, especially if someone has really worked hard, and I feel that that should be a good representation of the class, and that's what I do. Does that? So check again, maybe.
Yeah, because like, yeah, my final grade was, I saw it,
Okay, so
just I was a little confused.
So, yeah, ask me again. If, does this
Yeah.
does this clarify?
Yeah.
Yeah. So we are doing method of images. Oh, I didn't post the homework. Let's do it today morning. I promised earlier. Yeah, so there will be a homework 11. So this will be solving a differential equation. Very nice, actually. But number 4, mistake. We have midterm 3. And number 6. And the final exam. And again, this is in class. Assuming this really things don't get out of control next week. It seems like things are fine. But I actually don't know the details. Do you guys know the numbers or anything in the campus? Or?
I don't know for campus, I know that like.
Yeah, everywhere it is increasing, right?
Mhm.
Yeah, so
Checked this morning, I think it like went up slightly.
slightly, okay. Yeah, so track this. I'll decide this by next week, let's say, in case there is something going on, then I should decide accordingly. But by default, it's in class. Final exam, it's December 11. 2:45. But that's again 2:45. Did you check this? Or again, I was saying that before that that might be take home. Oh, actually, that has to be taken home, yeah, because it is after the Thanksgiving. Yeah, so that's not in class. Okay, so we were talking about method of images, and that was very. I gave it as a prescription. If you have a charge in front of a conductor, make an image out of it, and so on. Or why, right? I mean, how do you come up with this prescription? So we would like to solve this in detail by solving a differential equation, basically Gauss's law. We want to solve that. And the techniques that we will use here should be applicable in general, usually in so-called boundary condition problems. And you might have already seen it in quantum mechanics if you have done any quantum mechanics. If not, you will see this in quantum mechanics also. These are very general. If you're in engineering, these are problems related to heat or mechanical stress. Or most of these problems have very similar differential equations. Turns out that there are very few exactly solvable differential equations. So most of what we study in any part of science or anything you want to use, first solve it exactly, and then you go beyond, and then make sure that you make a check for in some parameter going to 0, or I get that 9%. So that is how typically things work. So that's why these show up in so many other places. So let's begin by writing our differential equations in that context. So electrostatics. So we will have to do this slowly in a few steps. So electrostatics. We will use ideas that you have studied before, like Fourier transformation and so on. And electrostatics, let's say differential equation differential equation for method of images. And one of the primary things why we want to use the Fourier transform is that most of the time differential equations or inhomogeneous differential equations are easier to solve in one dimension. By one dimension, I mean one parameter. Like it could be z, or if it's a sphere, it is a radial direction. So you want the final differential equation that you solve a one parameter problem. Two parameter, like two variable x and y, they're usually harder. It doesn't mean that it cannot be done. There are lots of problems that can be done. But typically at a very general level, if you want to use the standard techniques, then it is a single variable. So what you do is you get rid of the other variables by either Fourier transforming or legendary transforming or some transformation you use to get rid of the other variables. so that's the idea. So let's write the equations. We have with G is equal to rho, right? And D itself here is equal to epsilon times E. If you're in statics, usually these are frequency dependent quantities. If you're in statics, you're talking about zero frequency, so it's pretty much multiplication there. And we want to work with conductors. So that is del cross E is equal to 0. This implies immediately that E is equal to negative gradient of phi, right? And you typically solve for the potential and so find the electric field. So together, this is equal to, so that's a single equation. If I substitute this in the other, so this is negative gradient. So working like this, epsilon in general, this can be dependent on position, right? That is electric field. Sorry. Potential phi r is equal to charge density. You would like to solve this equation, right? Given any charge distribution. So our problem. So example, let's say, right? And maybe I should also say there are some always a differential equation comes with boundary conditions. Right? So there's boundary conditions. First is that as r tends to infinity, at very large distances, we require phi to be 0. The second is, so that's one of the conditions. And the second is that at an interface, that's what we did last time. And hat, what did we do? How do you say this? At an interface n dotted with d. So this is continuous. Let's say is continuous. It is equal. That's what I mean on the right side and left side. And we also have an perp dotted with D. Oh, sorry, E. Wait, no, E, D. E is continuous, which is equivalent to saying and and crossed with. So let me say this way. Is continuous. This means perpendicular to the interface. This means parallel. So for example, if you have an interface like this, and there is an electric field in here, and that's your n perp. Then by construction, if you do n cross E is always in the plane of the interface. So this is a way of saying that it is parallel to the interface. Right, that's your boundary conditions. We want to do a little further than this. We want to do method of images for conductors. Like if you have dielectric function 1 here, 2 here, which is more generic, then all these boundary conditions comes in. So let's also specify what are the boundary conditions on a conductor. On a conductor, again, if you have conducting perfect conductor, a conductor means a gold and copper are all conductors, but a perfect conductor is in the ideal situation where you really take the limit. Epsilon tends to infinity. First of all, a perfect conductor has epsilon tends to infinity. Epsilon of R is equal to infinity inside a perfect conductor. This is how we will put in our boundary conditions, which basically implies that if your n dotted with D has to be continuous, that means that since electric field or this is equivalent to saying this is because electric field has to be 0, right? Put the 0 inside a perfect conductor. If that is the case, then electric potential is equal to a constant inside a conductor. That will be our guiding. So in principle, it could be a constant V on the surface, but we will specifically do most of the examples. We'll hardly go away from that. We will do phi of R is equal to 0. So that's a grounded. That's your these are imposed in a sense. It's like when you first time study kinematics, you do acceleration due to gravity is 9.8. You don't completely realize why it is 9.8. So similarly, phi is equal to 0 at the surface of the conductor. So that will be our guiding. So our problem. Let's say. So the problem we are attending to involves this equation. So that this is your differential equation. It is negative gradient dotted with epsilon of R times. Did I write this correct? Something is wrong, right?
Yeah, I didn't know about the. Yeah, I didn't know about that. But
Yeah. Wrong, right? Sorry. Yeah. So D is equal to this. Electric field is this. So there's a gradient there.
I didn't know if that was like a chain rule thing, but I didn't.
No. That's just a mistake. A bad mistake. Yeah. Good that. Please, yeah. Tell me when glaring mistakes are there or asking. So, and that makes it a scalar, right? Otherwise, dotted with something, it needs a vector. So this is, and it looks very overwhelming. That's so a vector differential equation. It is hard, but we will do this. We will be able to solve this for very simple problems. And boundary conditions are the boundary. BC means boundary conditions are going to be phi r tends to infinity, phi is 0, and on conductor on conductor, on or inside conductor, right? On or inside conductor, a grounded conductor, let's say. Phi equal to 0. Right, that's all. Equation. Okay, great. So that's that should be very. In fact, these are just information, right? Doing much here. So let's. How do you attend to these problems? So let us do the following. Let's restrict ourselves to planar or planar geometry. We've been putting in a lot of restrictions just to simplify the problem. And what do we mean by planar geometry is that epsilon of r is only dependent on z. So it depends only on one dimension, z. Correct. In fact, like whatever we do will be applicable for this. The specific example we want to solve is like an example, for example. Example would be epsilon of r is equal to, in fact, this is still inhomogeneous. At least in Z, there is a lot of Z dependence in there. We want to do interface problems. Right? So we will say this is infinite for Z less than 0, and this is vacuum for Z greater than 0. Right. So example is, this is our method of images. So this is, so that's your conductor, perfect conductor on the left, and vacuum on the right. So that's how you will specify the problem. So inside in here, this is infinity, like the material electric property inside a conductor is infinity, which means that nothing can exist. No, there is no electric field, that of no charges, nothing. So this is, as far as electric phenomena goes, that's pretty much barren there. And vacuum is air, right? So that's the example we want to keep in our mind. So our differential equation then becomes gradient dotted with epsilon of z, right? So we want to remove the z dependence as much as we can. That's what we want to do. And now we want to separate things out. I have an R perp and a Z. What do I mean by that? And here also, charge could be anywhere. So this is R perp and Z. So what is R perp? So this is generally, this is X times I plus Y times J plus Z times K. That's your vector R. And if I were to write this as R perp plus Z times K hat, so let's now have this as K. let me write this as z hat, because I'll start using k for some other purpose, Fourier transform basically. So that's why it's z hat, x hat, y hat, z hat.
Is the equation supposed to be negative or positive?
Oh, negative. Thank you. Thank you. Thank you. Thank you. So it's clear here. What is r perp? R perp is equal to x in the x hat direction plus y in the y hat direction. It's very straightforward. Okay, so how do we proceed? We want to get rid of our r perp somehow, or we want to get a differential equation only in the z direction, but at the same time, it is meaningless to get rid of it completely, right? We cannot put it 0. So what we do is we work in Fourier modes where it's only the very variable characteristics that's there, the sources and other things, it will take care of this property here, or there's a translation symmetry. Another way of saying it is that there is a translation symmetry simply because it's a conductor. We want to capture that. So in principle, we don't lose any information, but we want to Fourier transform it. Right? All the R perp, we want to move it around. I think that's the way to say it. So it's like you want to work in a corner of the room, so you clean up things, so you're moving the R perp as much as you want. So what do you mean by that? So remember, there is an x and y in it, right? So another way of looking at this is x, this is y, right? So x and y. So I Fourier transform this. Right? Let's specify this better. So let me do this slowly. I'll do it in 2 steps. First, I Fourier transform in the x variable. So when you do a Fourier transform, you bring in a Fourier component kx. That's a Fourier transform of x, right? Divided by 2 pi. And these are unit vectors, eigenvectors, Fourier eigen functions, if you want, and that's plus, right? Plus I kx, right? And whatever is the Fourier transform, phi tilde is equal to now not dependent on x. This is now dependent on kx. This is what I mean by moving, getting away from the variable. I brought in the Fourier component, and presumably the Fourier components are easier to deal with. It is not necessary that always that's the case in every problem, but in this planar geometry, it turns out that it is easier to work with k instead of the derivative on top of it. That's what we mean. Just by the dependence here, I will know that, oh, this is my Fourier transform, so I'll stop putting in the tilde. It's understood that it's a new function, but I drop it, and it is implicit in there that it is, that's the case. Next, Fourier transform your y. So y of kx, comma y, comma 0. Again, Fourier transform it. So that's going to be ky, and this is minus infinity to plus infinity. And it will be done at a very formal level. What this means is that if I can solve for this Fourier transform, I will assume that the problem is solved completely. Right? Most of the time, this integral, even if you cannot you get a closed form expression, this is good enough because we know how a mode behaves. That would be the idea. So this is an expansion. This is a Fourier expansion of this. Even though we may not have a closed form expression for this, if we know how this behaves, that's a lot of information. It's like saying you know the vector, but you don't know only the vector components. You don't know the vector. So these are the Fourier components of this electric potential, and these are your Fourier eigenfunctions. Remember your unit vector and the components, right? So a vector is equal to ax in the I hat direction plus ay in the j hat direction. These are the components of a vector in the vector space. These are the Fourier components of the electric potential in the basis of Fourier eigenfunctions. So these are like the IJKs. So with that idea, so we again Fourier transform, we want to get rid of y also. So that will be e raised to I k y times y times, again this should be double tilde, right? This will be tilde, that's a tilde, that's a double tilde, but just avoid the clutter and it's not going to worry. Ky times z. Together, this will be y of r perp times z. These are two integrals. I have to substitute this in here. So that's two integrals. I'll write this as d2k perp over 2 pi whole square. So this is e raised to, or let me write this explicitly, no confusions. This is minus infinity to plus infinity, dkx over 2 pi minus infinity to plus infinity, dky over 2 pi e raised to ikx x plus iky y. And finally, this is phi of kx, ky, and z. Let me introduce the variable k perp. So vector k is kx in the x hat direction plus ky in the y hat direction plus kz in the z hat direction. But I am working with only kx and ky, right? So we never reach here. So this is k perp will be equal to just the two of x hat plus ky y hat. And let's also introduce the feature d2k perp will be a notation for dkx and dky, two variables. That it's like saying dx, dk, dy. This is equivalent to saying d2r perp is dx times dy. So in that sense, I can write this to be d2 k perp divided by 2 pi whole square. The exponential quantity, notice if k perp is kx I hat plus x hat plus ky y hat, and r perp is equal to x hat plus y hat, then k perp dotted with r perp is equal to kx times x plus ky times y, right? That's all. So that's nothing but k perp dotted with r perp by k perp dotted with r perp, and this is conveniently written as k perp. Let's see. And our goal will be to solve this, right? And the understanding is that if you know this, you pretty much know everything about this function, right? These are the components of the electric potential in the in terms of the Fourier eigenfunctions, and we will try to solve for this. Right? That's going to be our strategy. So the point is, put this in this differential equation and get an equation in z, one parameter or one variable differential equation instead of the vector differential equation. That we simply substitute it in there. Any questions at this stage? Should be reasonable. Right? Yes.
You only do the differentiation twice in k perp if epsilon doesn't have an x and y dependence.
Yes. Okay. Now what happens is that, okay, all this goes through for any. I can do the third one also at this point, right? So what's the more point here is that if there was an x and y dependence here, whatever I'm going to do next in the next two steps, that will not work very smoothly. Fourier transform of a single quantity and a bi-quantity, when you product two functions, Fourier transform, that gets convoluted. Look up, yeah, extra credit, right? Extra credit. Look up Fourier or just convolution, right? It's something called convolution. And in the context of, the context is Fourier transformation. So the simple to answer your question slightly more with a little more information, right? If you have phi of x, y, right? This is Fourier transform of, let's just, yeah, one variable, right? One variable, phi of x. This is dk over 2 pi e raised to I k x, and you have phi tilde of k, which means to say that if I know the vector components, I know the Fourier function. But what if you have psi of x times phi of x? Right? So very broadly speaking, this is 2 times this, right? So this is dk over 2 pi e raised to I k x phi tilde of x, or psi tilde of x. And then again, dk prime of 2k e raised to I k prime x times phi x, phi tilde of x. And you notice that there is a k minus k plus k prime, right? These are first of all two integrals. This is dk prime over 2 pi e I k plus k prime times x, and this is psi tilde of x and phi tilde of x. Or how do you see this? This is now. Let me make this y. Right? So see the convolution part. I want to make this x and y. But if you have x and y, then this is y. Like that's a simplicity that happens if it's the same. Right? So this is ikx and ik y, ik prime y. And what do you see the convolution? Why am I not seeing it? Because I'm supposed to get their psi tilde x, right? X and or k actually. Yeah, this should be k, right? Yeah. So this is k, and that's k prime. Yeah. So in general, x k plus k prime. Yeah. Okay. So again, let's go back to x. Sorry. Yeah, this is okay. So this is x, and this is x. And now if I want to write this as a single k and k prime, so if I were to substitute k prime is equal to k plus something, k double prime, you notice that this is psi tilde of k times phi of k plus something. So this overlaps itself, right? So there is psi of k, and then you multiply it with something else. And that's called a convolution. think I'm not able to do a good job of explaining this. It's a neater concept. So basically, the components in that space mix up completely. So it's too complicated. But if this was not having that X and Y dependence, then this goes smoothly and there is no issues there. So that's the idea that if you have this no X and Y dependence in there, the Fourier transform of this is easy. Yeah, maybe I'll give a better answer. Yeah, or as we are going, probably we'll see it. Like whatever, I think another problem you should ask is whatever we are going to do next step, like 5 steps or so. What will change if there was an X and Y dependence? What will not work? I think that's a very question. And whatever we are doing will not work or will not be useful if we do. So let me quickly proceed then. And that is where the symmetry also comes in. The planar symmetry makes it so very raw and efficient. Okay. So that's our solution. We want to write our equation in terms of this instead of this. Right? So let's do a gradient. The gradient of phi of r curve of z would be, so we want to write this differential equation. So it will be the same as, substitute this in here. The 2k per 2 pi whole square e raised to I k per dotted with r per, and then phi k per, let's see. Notice what is happening here. There are 3 pieces here, right? So let me write that down. So this is I d by dx, x hat d by dx, plus y hat d by dy, and that is z hat d by dz. Acting on the 2k per over 2 pi whole square. And this is e raised to ikx times x plus iky times y. And that is phi of k per dotted with z. Let us see where are the things this differential operator will act. X will act only here. That's the only place where x sits. Y will act only place where y sits. That's a simplification method. There is only those 2 places. If there was, when the next one comes, x and y can penetrate that. So that will be the simplification that will come in. But z will go in there. Right? Z will go in here. That's the that's what is going to happen. So, but once it acts on it, kx comes down. So that's dependent on the integral. So I'm going to move this integral out. This can go in, right? X, y, and z can go through this integral because the integral doesn't depend on that. So let's do that. So this is d2 k per. So at this point, there are manipulations, but we are going to reach a different, the goal is to reach a differential equation. When I hit this derivative with respect to x, I get an ikx. So this is x hat times I times kx. Is that clear? When I take the derivative acting on this exponential, ikx comes down. The next one is y hat. It acts on this, iky comes down. And the derivative d by dz has to act on this function. Unless I know this function, I cannot do much. Right? So I keep that there. So that's there. And rest everything is phi k perp z. This is nothing but k perp, right? So this is I k perp as a vector. That's what we defined as kx, x hat, ky, y hat. Once it's in this form, I can actually go through the exponential because these are not differential operators anymore. Right? That's a very classic thing about Fourier transformation. It makes it algebraic instead of a differential equation, or instead of differential operators. Now I have algebraic quantities. So I can go through the exponential. Still, I cannot do the derivative with z. Everything has been written in terms of z now. This is I k perp dotted with r perp times. So this is I k perp plus z hat d by dz of this function. Doesn't seem very useful, but the point is the next operator will make this a differential equation. Even this is very useful because instead of 3 differential operators, we have only 1 differential operator, right? So no doubt that this is simple, right? It's only 1 minute, so let me, I will actually come and complete this next time. If I were to do the next differential operator, so let's say this is, let's say just attempt this, attempt at home, but we will do this again since it's important. I want to do this. So this will give you, so minus del dotted with epsilon of z of phi will give you actually e2k perp over 2 pi squared e raised to ik perp dotted with r perp. So this can be extra credit, but don't worry if you're not able to do it. It's only attempt, right? Extra credit. Just attempt on this. This will give you minus k perp square because ik perp, 2 of them will come in, and then it will be an epsilon z. So that's epsilon z times k perp square. And the other part will be, write it as a proper differential equation. This is d by dz of epsilon z and minus epsilon z times k perp square times phi of k perp of z. Okay. Notice the structure of the differential equation coming up. We haven't set that equal to 0 yet, but that's how we will. Thank you.
So the Fourier transform